asked about is 32. And the question on the document was, how do you find out what the pressures are? Okay, the key to that is this. It's asking about the equilibrium constant. So what do? Our good old friend, the Rice table. Sorry, just looking up what the reaction was because it's scrolling up. So we start out with 1 here, nothing, nothing. All the coefficients are 1, so our change can just be minus x and then plus x. So our equilibrium pressure are 1 minus x, x, and x. Don't forget that Rice tables can be used for both concentration and pressure, so it's a nice, easy thing here. So then somewhere it tells us that the equilibrium pressure is 1.4. Oh, we found that in number 31. So we can take all of these equilibrium pressures, add them together, and you can do this in parentheses if it helps you see where they came from. I'm doing all of the equilibrium pressures, so PCl5, PCl3, Cl2, and equaling that to this total. When you solve that, you get 0.4. So going back here and plugging in X, we know that the pressure of Cl5, or PCl5 I should say, 2 P's, is going to be 1 minus X, so that's 0.6. The pressure of PCl3 is just X, and the pressure of Cl2 is also X. So then you just plug that in to your Kp formula. Or expression, I should say. And you can do that math out if you want, but it's pretty clear it is going to be less than 1. So our answer would be B. Next question is 34, and I'm really glad someone asked about this because it does, when you look at the answer, look like you're dividing by 10, but that's not what you're doing. The easiest way to do this is through stoichiometry. But before we do a stoichiometry problem, we need to look at what the question is asking and do a little bit of adjustment. So here it says, how much heat is released or absorbed when 0.05 moles of CO2 is formed from KCl? So that's not what our reaction is showing us right now. It's showing us CO2 being used up and forming KCl. So what we're going to do is flip this reaction so that it mimics what the question is saying, right? We need CO2 to be formed from KCl. So we're going to flip this reaction around. And then what does that do to our delta H? It changes the sign. Okay, so now you just can set up a stoichiometry problem. You can set it up, you guys are very familiar with these stoichiometry. You can set it up by starting with this, you can set it up by starting with this. It doesn't matter, you will get the same answer. Okay, so I'm going to start with our delta H, 437 kilojoules per mole reaction. And then for every 1 mole reaction, how many moles of CO2 do I have? I just look at the coefficient in the reaction, so it's a half. And then I'll end with the 0.05 moles of CO2. Okay, so that's the math you're doing here. You're not dividing by 10. It's just that when you do out this math, it comes out to be divided by 10. Okay, but there's no 10 anywhere that you were supposed to find in this problem. That was magic. It's actually the 0.05 divided by 1/2 that comes out to be 10. Okay, divided by 10. So when you do this out, 437 times 0.05, and then divide that by 1/2, you get 437 kilojoules. And since that's positive, we know it is absorbed. So our answer will be C. All right, the next question is 35, which also relates to this equation and table. So I'm just going to erase all this extra stuff we did to solve 34. 35 says, what remains in the reaction vessel after equal masses of K and Cl2 have reacted until either one or both of the reactants have been completely consumed? So what does that say? When you think one or both is consumed, you should be thinking limiting reagent. Okay, great. Let's do a limiting reagent problem. For limiting reagent, we find the moles of each reagent and divide by the coefficients, pick the lower of the two. We don't have moles. All that it says is equal masses. Remember, in the first part of the questions on this test, I said, if you have equal moles or equal masses, you can just use a variable, or you can just pick a random number. Okay, personally, I think the random number here works easier, but if you wanted to use a variable, you could do that too. I'm going to use 10 grams because I think that's easier. So, because I'm used to going from grams to moles all the time. So then for K, you would take your 10 grams, your molar mass of K is 39. So that comes out to, whoops, this. And then of course you divide by the coefficient, but the coefficient for K is 1. For Cl2, you would do the same thing. Molar mass of Cl2, don't forget it's 2 of them, so it's not 35, it's 70. And then divide by the coefficient, which is 1/2. So that comes out to 0.285. So then I look at this number and this number, pick the lower of the two, and that's the limiting reactant. Okay, so we automatically know K is the limiting reactant. So let's go back to our problem. We can get rid of anything that has K in it. And we also know that they did not have equal amounts, equal moles, okay? Equal masses is not the same as equal moles. Remember, to compare two substances, you need moles. So they're probably in this question trying to throw you off by saying equal masses so that you would think they would both run out at the same time. But they're not. Plus, they don't have the same coefficients. So hopefully you didn't fall for either of those traps. So it is not going to be KCl. It's not that they're both going to run out at the same time. So the answer must be C. And that is why Cl2 is there and not K, which was the question on the document. Okay, I'm going to erase all this because the next question that was asked was 36, which is the same set of situations. Okay, which of the values of delta H for a process in the table are less than 0, i.e. indicates an exothermic process? Okay, this question is testing you, part of it is testing something very important that hopefully you remember. Forming bonds releases energy. And we know that means it's exo. Breaking bonds absorbs energy. And that means it's endo. So this one doesn't ask about V. Okay, so we're only looking at W, X, Y, and Z. So the first one, so you're looking for something that is exothermic. Okay, so we know that if anything is forming bonds, it needs to be exothermic. So let's see, are any of these for forming bonds, taking two separate things and putting them together? Yes, this one, right? That one is forming bonds. That is definitely exothermic. So whatever our answer is, it has to have Z in it. Unfortunately, every single one of our answers has Z in it, so that just gets us absolutely nothing. Okay, are any of them just breaking bonds? Because then we would know that one absolutely cannot be included. Yes, this one right here is going from Cl2 to just two separate Cls. So that one has to be endothermic. Okay, since that one is endothermic, anyone that has X included, we can get rid of right away. That does actually help us. Okay, so now we need to just figure out about Y. Y taking Cl and adding an electron to make Cl minus. There's a couple different ways to think about this. Remember when we in first year chem, which I really don't expect a lot of you to remember, we said, why do elements bond? They bond to become more stable. They calm down when they become more stable. They release energy because they calm down. Anything that's going to be kind of forming its perfect octet by accepting an electron is going to be calming down, it's going to be more stable, it's going to release energy. So this does release energy. Okay, now you don't need this to answer the question, but you might be saying, well, what about K? Isn't K also forming its perfect octet? Yes, and in first year, it was easy just to say that. There's more going on here in terms of releasing an electron versus accepting an electron. So what I would probably think of it as is it's not a bond, but you can kind of compare it to a bond. When Cl is accepting an electron, you can think of it as Cl forming a bond with the electron, releases energy. When K is giving up an electron, it's breaking the bond with the electron, so it would release energy. So like I said, in first year, we didn't really get into that. Here, that's kind of how you should think about it. So if there was an option that included W, we would take that out because releasing an electron is kind of like breaking a bond. You can think of it that way. All right, and then the last one that was asked about with this little group of problems here was 38. 38 is, oh, the dogs have something to say about that. Wait a minute. Okay, I think they've calmed down a little bit for now. 38 is a Hess's law problem. We're going to pick whatever of these we can add up to get to this. And then that will be our delta H. Okay, so if we take this one, Cl2, to give 2Cl. Oh no, not minus. And then that's going to be X for our delta H. That would get us this, and then we can take the one right below it, but we're going to need to multiply it by 2, right? Because we're going to want 2Cl to cancel. Whoops. So then that would be 2Y for delta H. These would cancel, and you'll end up with Cl2 plus 2 electrons. Gives you 2Cl minus, which is what you wanted. So then all you have to do is add the delta H's together. So your answer is going to be C. All right, next question was 39. 39, I gotta tell you, it's a difficult question. Hold on, I'm gonna try to get Walter to stop screaming.